Today we're tackling a HackerRank problem called Happy Ladybugs. This is an easy difficulty problem. As usual, we'll review the problem. I'll give you some time to do it on your own and then come back with my solution. All right, here we go. Happy Ladybugs is a board game having the following properties. The board is represented by a string, b, of length n. The ith character of the string is denoted by b of I. There are a few characters it could be, but there is the underscore, meaning that the ith cell on the board is empty. Or it could be an uppercase English letter from A to Z, and that means that it is a ladybug of that particular color. It's just kind of a label, essentially. The string will not contain any other characters, so it's only going to be either letter, capital letter, or a underscore, meaning empty. So a ladybug is considered happy only when its left or right cell is occupied by another ladybug having the same color. In a single move, you can move a ladybug from its current position to any empty cell. So given this information, determine if it's possible to make all the ladybugs happy. For each game, return yes if all the ladybugs can be made happy, or no otherwise. You can imagine a string YYR underscore meaning empty, B empty, BR. And you can potentially move everything around such that you can get two Y's next to each other, two R's next to each other, and two B's next to each other. So in this case, all the ladybugs are happy because they're next to a ladybug of the same color or label. All right, so that's the idea. I'll give you some time to do it on your own and come back with my solution. Good luck. Before we go into the code, I do want to get an understanding of exactly what's going on with the patterns that we can start recognizing, which will help explain the solution. First, let's see an example of a potential game and kind of walk through some of the steps and see what we can observe. So here we have R, B, Y, and an empty space, and then Y, B, R. And so let's visualize it, make it a little bit nicer. And so we see these colors and we notice that there's an empty space. So can we move things around so that we have all of the colors sort of next to a partner so that they're all happy? And the first observation is that as long as there is one empty space, we can move any color anywhere and in any order that we want. So first we see we have this empty space. Well, we can move the blue out of the way and put in the empty space, move over the red, and now that's matching. And now we can kind of get rid of that blue again, get the empty space where we want, put the yellow there. And we're basically satisfied at this point, but we can also just move it over even more if we want. We can do pretty much anything we want. And here this would check out, we would say yes for this. Here's another observation. We should recognize that if there is a single label or color, then there is no way that that ladybug can be happy, and we could essentially return no just from that piece of information. All right, so the last observation is what happens if there are no available spaces to make a move? The sequence must be valid as is. We must verify if the current state of the game is satisfied, if all the ladybugs are happy. If they're not, then we know that we would return no in that case, and if it is, then we would return yes, obviously. But we know that we cannot make any moves in this case. All right, let's get to some code. All right, so today I'm going to be coding in JavaScript, but I will be sure to leave a Python solution in my description. So first, we're going to establish a variable called hasSpace. This is just a true or false to see whether or not there is a single space available. If there is, then we know that we can move things around any time we want, at as many times as we want. I'm going to create a hash map, or in Python here it's called a dictionary, and I'm going to just assign the label as the key and the count of that as the value. So I'm just going to go through the string one time. We're going to see if that label is an underscore, because we know that that means that there is a space available, and so I can set space to true. And then I'll just continue at that point because I just want to kind of skip that. I don't want to add it to the count or in the store. If we get past this logic, then we know that we have either a color or a label, and we're going to just add it to the store. If it's not in the store already, I'm going to establish it here. I'm going to get the key as the color itself, establish 0 as the starting point. After that, we know that we definitely have it in the store, and then we could just add 1 on top of whatever is currently there. So we're just keeping track of a running count of how many times that particular label or color shows up. Once we're done with that, we have a nice dictionary of the color with its associated count. And now what we'll want to do is to check that other observation, which is whether or not there is a single label. If there is a single label, we know that there is no way that it could ever be satisfied. There's no partner for that ladybug to be happy with, right? So I'm going to use object.values to get the values from the store. So this is all the counts essentially. And I'm going to check to see if any one of those counts, if even one of them is 1, then we know that there is no way that we can satisfy the problem, and we would return no. Otherwise, we know that all the labels are 2 or more, and so we would then check, okay, is there space? This is the has space that we established up here. We can move everything around all we want, and so we could just return yes from this. So past this point, we know that there are no spaces, and all the labels have 2 or more counts. This means that we need to determine whether or not the ladybugs are kind of already in a happy state. If they're not, then we return no. If they are, then we return yes. One thing we can do to kind of like short circuit this is to check to see how many keys there are. If there's only one color, then we don't need to do anything because it's just the one color and they're all happy because they're all the same color next to each other. There are no spaces. So we can just return yes in that case. Otherwise, we know that there are multiple colors, and then in that case, we would have to kind of go through and check. Now, here we are, the logic of going through each ladybug and checking to see if it's happy. I'm going to create a for loop here, and I'm going to iterate through the length of b, and I'm going to first grab the sort of label, the current label that we're at, b of I, and I'm going to need to check the left and right to make sure that either one of those, it needs to be the label, the same label essentially. So I'm going to establish this variable, the previous label, which is essentially on the left, and the next label, which is essentially on the right. Here I'm doing a bounce check. If I'm literally on the first element, there is nothing to the left of it. If I do I minus 1, it would be less than 0, and that would be problematic. Here I'm just making sure, oh, if I minus 1 is possible, then we can grab it. Otherwise, it would be unchanged. It would stay null. I'm doing the same thing for the right side here, essentially. On the very last element, there's nothing to the right of that. And here, I'm just doing my check. Is it the case that the current label doesn't match the previous label or the left label? And it also doesn't match the right label. If both of those are false, then we know that Ladybug is essentially surrounded by things that are not like it, and therefore it is unhappy. And so we can actually stop here and just return no immediately. The second we find a Ladybug that is not surrounded by at least one thing that is like itself, we're done. We can stop. There's an unhappy Ladybug. Otherwise, we got through this entire for loop, and none of them were unhappy. So we can just say yes, we can return yes, and essentially they are all happy. So let's run some code and see how that works. All right, and let's submit the code. Hey, there we go. It looks good. All right, let's check some time complexity. The first time we go through to establish the dictionary, we have a big O of N. We go through each letter. Now, the only time we have to go through big O of N again is to sort of check each individual ladybug once we have no choice but to do that. So technically we have a big O of N plus another big O of N, but that is essentially reduced to just big O of N by itself. All right, folks, if this is the kind of content you enjoy, please make sure to like, subscribe, do all the good things, and I will check you next time. Take care.